谢谢谢谢大家好。其实我是刚从北京飞过来，所以可能看这样的观众，我就以为可能应该用中文。但是因为我现在在美国，所以我会换成英语。如果后来你有什么问题想问，用中文问也行。The rest of this talk will be in English because we're here in America, and I guess English also makes a lot of sense for me. One moment. I'm learning a little bit about the physics of this. You're adjusting the volume control. Thank you very much. So we're actually seeing an example of applied mathematics right now. This is a feedback that's happening, where he's trying to adjust it so it's just loud enough for you to hear, but so that doesn't get into my microphone. But that's okay. I'll use geometry. I'll use the fact that those are facing that direction. So I'll stand back here. Right. But continuing my introduction. I was born in the United States, and I grew up entirely in the United States through the US math competition. And through that, I learned that math is more interesting than just doing some homework problems. But for today's talk, actually the first part is not going to look like that kind of math at all. For this, could I also request to borrow the HDMI line? Yes. I want to be careful not to step too far forward, or else I will start the feedback. So let me put this in. One moment.
Let me know you need help.
不需要。Great. Okay. Good. So for this talk, I actually want to start with something that looks like a game. I brought some dice. What do we usually do with dice? You roll them. What do you mean gamble? You just have to go to Armold for that. I'm kidding. Actually, the Armold is held in Las Vegas, but the students are not allowed to gamble. They're not old enough. So you usually use dice to roll them. Now, it's because we might want to play some kind of a game. Actually, at this point, I want to say there might be some people in this audience who have seen parts of this talk before. My request is, if you have seen any of this talk before, please don't give away any of the secrets, because we want everyone else to be able to enjoy. And if you've seen it before, you'll get to see some different angles that you might not have noticed before. It's like watching a movie for the second time. So, what we usually do is we play games. Why do we use dice for games? Yes? Because it's random. You want some random thing. This is the most random thing you can find. You want a random outcome for the game. So let's think. Suppose I want to make a game with two players. One player on each side. Can anyone think of a way to decide? This person rolls a die and gets a 5. This person rolls a die and gets a 1. Who wins? It depends on the rules. I heard it depends on the rules. What do you think is a reasonable rule? Bigger. I heard some people say bigger. I heard some people say smaller. Maybe the smaller one. People who like smaller, maybe they like to play golf. It's okay. There are rules, right? But it's a reasonable rule to say, look at the numbers and see which one is bigger or smaller. Those are the same game, effectively. But I don't quite like ties. So I want to play a game where we're less likely to have a tie. Each person will roll the die 4 times. Each person will roll the die 4 times, and each person will get 4 numbers. How can we decide who wins if each person has 4 numbers? Does anyone have an idea in the picture? Yeah. Add them up together and see who gets the bigger one. I have a question. How many people here were thinking of that kind of a rule? How many people here were thinking, add them all up, see who gets the bigger one? You'll see a lot of people raise their hands. And, should I be louder? Is that what you mean? Oh, I understand. Okay, that's an easier way for me to be louder. Okay. But I see many people are thinking, add them up and see which is bigger. And the good thing is I didn't plant him there. I didn't tell him what to say. In fact, I've never talked to him before this. But it's a very natural rule. Natural rules are the ones that are the most interesting to think about. That's actually one reason why sometimes homework problems don't seem so interesting. Because you might be wondering, who cares? Why do I need to do? You might think, why do I need to do this kind of problem? I don't know what it's for. But here in this game, this is a game that everyone might think of. So this is a natural game, and it's worth thinking about. In fact, even though I didn't place him there, that's my next slide. I read your minds. This is the most natural game you can think of. So again, 2 players. Each player throws their 1 die 4 times. Each time, they will get a score that's equal to the number on the top of the die, and whoever gets the higher sum of the 4 scores wins. Does everyone understand this game? Very simple. Can I have 2 volunteers? Yes? Who wants to represent this side?
Oh, right here.
you might have seen something before. In the back, right there on the edge. Yes, you. Okay. But don't worry, we'll need more people because I'm a mathematician, so I'm very bad at arithmetic. It's true. If you do math for a while, you just think about thinking and you stop doing calculation. So could I have 2 people who are very good at adding numbers who can keep score? You seem to want to keep score. Come forward, please. On this side, who wants to keep score? Is that a hand on the edge? Come on. Okay. So whose score are you keeping? Whose score are you keeping? Over here. Whose score are you keeping? Who do you want to keep score for? All right. Where's the other person? I thought there was another person coming. He's not coming anymore? Did he change his mind? He changed his mind! Okay, this floor is open now. Over there. Yes. Please come forward. And I guess that means you're keeping this score? Is that okay? And I guess you're keeping this score. Let me say a little bit more about it. You're not allowed to roll the die like this. I got a 6. Not okay? So when you roll the die, it should go across. Actually, if you're rolling the die, can you be on this side? If you're rolling the die, can you be on this side? If you're keeping score, be here. So you're on that side, actually. You're rolling the die so that you're against each other. You're keeping score over here. Don't fall off the stage. And when you roll the die, it needs to cross the halfway. Is that okay? Okay. And also, you guys are keeping score. That means you need to pay attention to the die as it's going, since it goes far. Also, every time just switch dice. Because yours goes here, yours goes there. Does it make sense? Okay, it seems to make sense. Let's go ahead. First round. Let's go. It's okay if it falls down. It's okay. Who's keeping score? You're keeping the score. Why don't you run over there? You're supposed to keep score. And you keep the score on this side, and you see the score already, right? Yes. So put the dice back. Switch dice. Remember to switch dice. Switch dice. And now please tell me, what was the score on this side?
2
versus
4.
2 versus 4. Second round. Let's go. It's okay if it falls. It's okay if it falls. What's the total? What's the sum? What is it? 4, and what's the total?
6.
4, so a total of 6.
What?
1, which is a total of 5. I hope they did the addition right because I'm not doing it. Oh, you seem to be quite happy. Third round. Let's go.
3, which gives a total of 9. 1, which gives a total of 6.
9 versus 6. Fourth round. Let's go. There's still a chance. It's okay if it falls down. Oh boy. Ooh. That's a 3.
3, which gives a total of 12. 5, which gives a total of 11.
Close. Okay. Great. But actually, who wins and who loses? That was not the point of this game. Thank you. Please stay. You guys, please stay. The point of this game was to feel what the game is like, so that we can talk about it. And now I'm going to ask some questions, and anyone can help to answer these questions in the audience as well. I'm asking these 4 to stay here, so they can be your eyes and your hands if we ever have to ask any questions about the actual game stuff. So the question I want to ask everybody is this game fair? Okay, I heard both yes and no. And in math, we can't just have an answer, we need an explanation. So does someone want to explain yes? You want to explain no. So does someone want to explain yes? Could I have someone with a microphone to help bring around? Somebody who wants to explain why yes, it's a fair game on this edge right here. I see, like on the 4th row. Can we get him a microphone? He'll just yell, he said. It's really loud.
The game is fair. There's no advantage for any player.
Because there's no advantage for any player. Why?
Because they all have the same dice.
Because they all have the same dice.
And there's like, it's not like one dice is like has like an extra number.
And it's not like one die has an extra number. Thank you. Thank you. And what I will say is, how does he know that? How does he know the dice are the same and none is an extra number? In fact, nobody here ever checked. See, now they're checking. Okay? Still, it's a good answer, but it's contingent on a fact which has not been verified. They don't know that the die doesn't have a 7 on it. Oh, does it have a 7?
No, it doesn't.
Oh, okay, so it doesn't have a 7. But still, that's good. But I still want to hear more answers. You said no. You want to define why it's not fair?
It's not fair because the rolls are random, so like it wouldn't like the percentages and chances wouldn't be the same. So like I guess the chances would be the same, but like it wouldn't be fair because it's based on luck.
Okay, so this is something very interesting also. This has to do with definition, right? The question is, what does fair mean? That's a philosophy class now, right? But actually, I also agree with him because there were many times in my life that I said, what? All these decisions are just based on chance, not whether or not I'm actually good. And I always felt bad if I lost something which was based on chance. So I can very much sympathize with that sentiment. For this talk, though, since everything we do in this talk is about chance, what I will ask is, I will not ask is it fair. That's philosophically difficult. Instead, I will ask, do both people have the same chance of winning? Now he says yes. And you said yes also, but your answer was contingent on some scientific experimentation on whether the dice are the same. Does anyone have a different answer or a different explanation? Here in the corner, somebody wants to say something. So I just heard what you said, so I'll echo. Oh, you want to say it again loudly? Hopefully it won't break it.
It's because they switch the dice each time, so you should go say that.
So because they switch dice each time, it's okay even if the dice were different. That's why I forced them to switch the die each time, because each person had 2 chances on each die. For example, imagine one die had all 7s and the other had all 1s. What would the scores be at the end? The same, right? Because everyone would get a score of 16. So it's actually okay, it's definitely fair, because they switch dice each time. So is everyone happy? Oh, this guy wants to say something else.
Every time an object interacts with another object, they always switch some atoms. So each time the chances of getting one of 6 numbers is different.
Okay, so this guy is trying to say, maybe theoretically it's not exactly fair because the state of the world has changed. Some black hole, which is 50 billion light years away, has moved a little bit, and so the gravitational fields are slightly different. It is true. They are not exactly the same. However, I think maybe I need to correct my question a little bit more and say, do they have almost exactly the same chance of winning? Where the almost exactly means within 0.0001%. Within 1%, I'm happy. Within 1%, I think they're okay. So I think we got this. We got all the answers I wanted to this question so far. Which is that it is indeed fair. Oh, this guy seems to really want to say something. What do you want to say? You just shout loud because we don't have a microphone there. Okay, he asked, what does it mean if we say something is fair? How many rounds are they playing, right? So here I'm really just talking about play 4 rounds. They change every time. And so in this game, actually the chance of each person winning is about 50%. So this one's okay. But now I'm going to say, the reason I brought this game, and actually I brought these, is because I want to teach another lesson, not a math lesson. See, here's a practical lesson. If somebody shows up with a game and says, hey, I've got a game for you to play, and also brings their own dice for you to play the game, you shouldn't trust them.
Usually the game is rigged.
This guy already learned the lesson. He already knew the lesson. Usually the game is rigged. And I'll tell you, actually these dice that I brought you are strange. I specially manufactured them in Hong Kong. They are strange dice. They're not normal. Now they're curious. What would you like them to do? They're going to do your experiments for you. If you would like them to check anything, please raise your hand. Yes?
I want them to check that the sum of the numbers on opposite sides equals to 7.
You want them to check that the sum of the numbers on opposite sides equals to 7.
Wait, the sum of these 2 is 3 and the sum of these 2 are 11.
What? So they said that the sum of certain two opposite sides was 3, and the sum of certain two opposite sides is 11. Okay, but are they the same?
Yeah.
Yeah, okay. That's true. So what? So how does that change anything? Does that change anything? No. Okay. Actually, I want to say one more thing. Since when was that supposed to be true anyway? Where did you learn that? Where did you even learn the fact that the opposite side is supposed to add up to 7? You're not sure, you think you read about it somewhere. Actually, that's how I learned that fact too. I just read about it somewhere, and I was just curious, is this really a fact? Okay. Back there in the 4th row. He wants to check a physical thing. He said, you want to say it again? You have a microphone.
What's this thing? It's like part of the dice.
He asked, is part of the die heavier? Is one of the sides heavier than the others?
How are you supposed to find out?
That means no. so not noticeably. The answer is not noticeably. Okay. There are still more people with hands. Oh, over here in the red. Why not? Good. He wants to check if there are any special rounded corners.
Yep, there are special rounded corners.
All the corners?
Yeah, all of them are rounded.
But they're not special.
So they're both, all of the dice have rounded corners in the same kind of roundedness. Okay? In the blue, right there.
Well, we could just force them to throw each die 100 times and see if the chances are the same.
He wants to try to throw each die 100 times, see if the chances are the same. How about 102? Actually, does anyone know why I said 102? Does anyone know why I changed this 100 to 102? Actually, there's a really good reason. Why did I say 102 instead of 100?
By 6.
It's divisible by 6. How do you know 102 is divisible by 6? This is a quick math thing. How do you know 102 is divisible by 6? Well, let's get one side or something.
It's divisible by 3 and 2.
It's divisible by 3 and 2. How did you know it was divisible by 2? Oh, God. Okay, how did you know it was divisible by 3?
Because the sum of the digits are divisible by 3.
Yeah, there's a nice math fact. If you want to learn more about these math facts, I encourage you. You've got lots of opportunities to learn this, but 1 plus 0 plus 2 is 3. That's a multiple of 3. Boom, it's a multiple of 3. And it's even. Sorry? You can also do that at 9. This guy's really taken a lot of these math classes.
Yeah.
Yes, okay, so good. So these are ideas. Yours is an empirical method. Just try it and see if experimentally it works. Cool. I'm just going to take one more feedback, one more idea from the audience in the back. Oh, they're like facts. I see there's somebody there. Yes? And then I'll keep talking. Right there. I see somebody raising their hand.
Yeah, well, let's take out some of the keys actually on this side there. And then behind.
Okay, so my question is to make sure that there is no some sort of magnets underneath the table.
Oh, are there any magnets underneath the table?
There's only a water bottle.
There's only a water bottle and water's not magnetic.
Is there any magnets on the dice?
Is there any magnets on the dice?
It looks kind of like that.
What?
It kind of looks like that. It's like
But that wouldn't matter unless there's another magnet.
maybe the dice are attracted to each other.
Maybe the dice are attracted to each other, are they? Let's find out. No, they're not. So I think we now know. Well, I mean, if you really want them to be attracted, this is how I would do it. They're attracted to each other. No, they're not. Okay, sure. Okay, so I think we did enough testing. We have come to the conclusion that really there's nothing that we can see that's strange about the dice, except for the very first thing that was said, which is that this somehow violates our conventions. But we haven't found out that it matters. However, what I'll say then is that's enough for the experimentation. So thank you, the 4 of you can return to your seats. Let's thank them for being brave. And I want to start talking about these topics. Okay. Let me tell you where this whole talk came from. So this entire talk topic originated from me being on an airplane from San Francisco back to Pittsburgh after giving some talk, probably at one of these local math competitions. And I was on this airplane because about 3 years ago, 2 or 3 years ago, every week I would release some interesting problems that have something to do with real life. And the way we would do this is some people in my office would tell me, hey, Po, think about this real life topic. Might have been like the Super Bowl or something. And that week, it was called board games. So I thought, yeah, I read a long time ago that the opposite sides of the die add up to 7. That sounds like it would make a good topic. And then I stopped and said, wait, but I don't know why. I only know I read it somewhere or heard it, but I don't know a good reason. And then that started to bother me. If you are a mathematician, or if you do research, or if you like to understand how the world works, if there's ever something that you know but don't understand, it bothers you. It bothers you. You see, knowing is different from understanding. I can know that gravity is like 9.8 meters per second squared, but that's different from understanding Newtonian mechanics, right? Sorry, this is not a high school audience. I'll use other topics. But like dice is the same thing. I can know a fact but not understand why. So then I started to think about it. Actually, this is a very fun topic which I like to give in these talks because nobody knows the answer. In fact, if you go to Google and you Google it, why do opposite sides of the die add up to 7? It's great. You get answers like, because they do. You get other answers like, because it's more fair. And then the follow-up question says, why is it more fair? And the answer is, because it is. You get answers that say things like, it's always been this way. That's why it is, right? You get other answers like, nobody knows. Actually, when you see something like this, it's fun to think about. The most fun questions to think about are the ones where there's not a clear, well-known answer. In school, you're often used to doing problems where there's like, the way to do it. Those are boring. I don't like doing something where there's only one way to do it and I have to do it that way. If that was how I thought math was, I wouldn't be doing math today. What math is about is it's about finding your own way to do something. And better, if you can find your own way to do something that no one knows how to do. So then I thought this was a good challenge. Why do the opposite sides of the die add up to 7? Can I think of a good reason? And in fact, this answer is so little known that in this room, most of the parents don't know this either. That makes this a more fun talk because students will answer, and then we'll also let parents answer. This is great. Today, you might actually find the answer because I've given this talk to, I don't know, like 10,000 people already. And so, actually, it's so much so that today, if you search for my name on Google, you know how Google auto-completes? Sometimes you type Po-Shen Loh, one of the auto-completes they offer you is nice. So I guess I became well known for this. But let's now bring everyone in to think about this. I want everyone to get a chance to taste what research is like, what thinking about an unknown problem is like. Does anyone have any ideas of why maybe opposite sides of the die add up to 7? If you already knew the answer because you saw my talk or read it somewhere, please don't give it away. That would be lousy for everyone else. But if you want to participate in brainstorming, it's okay if you don't have the right answer. We'll build off of it. Over here. Why do you think? Because it looks nice. You know what? There's some value in that answer. It looks nice. It has an idea of symmetry. People like to draw things that are symmetric. People like to design things that are symmetric. There's a reason the car has 2 wheels on each side. Actually, no, that's a physical reason. But anyway, generally people like to have things that look nice. That's one possible answer. We're going to keep building though, because actually that would be one part of the answer. The answer is more sophisticated than that. Over here, okay. So I'm saying this, what he just said, I'm saying louder. He said the word average. He said the sum of all 6 numbers on a die is 1 plus 2, thank you. 1 plus 2 plus 3 plus 4 plus 5 plus 6. The sum of all 6 numbers on a die is 21. And there are 6 sides. And the average of those 6 numbers is 3.5. Even if you don't have any advanced math background, you can see by the average of 1, 2, 3, 4, 5, 6 is 3.5. And he says, then maybe the 2 opposite sides, just make it like twice the average, right? Because like, why not? It is somehow maybe more balanced. That's a good idea too. We're going to use that somewhere in the answer. Anyone else have other thoughts? Yes, in the front.
7, each black dot has a hollow space.
Oh, please, let's say it here.
Each black dot has like a hollow space, so each 2 sides have the same amount of hollow spaces. What's the other?
Oh, so he's using the physical nature of the dice. He's saying that these dice are made where the dots are these hollow spaces. People who are in the front, is that true? Yes, so you saw. These are the dice where there are some hollow spaces, and he's thinking maybe it has something to do with the physics of the die, and maybe the hollow spaces do something to the die. Let's keep building on these ideas. I like that everyone's saying these ideas because they're giving us things that other people can build off of. More thoughts. A parent. Oh, okay, here. Let's get the microphone.
Actually, I do. My idea is building on the top of that one. It's actually the whole size is different, so that the mass it's almost the same on each side.
Okay, thank you. So I want to say that combination of those two answers was the first explanation I thought of. Okay? So I was sitting on the airplane and I was like, aha, that's what it is. Actually, you can probably tell by now in this talk that I talk about physics quite a lot. That's because a lot of math was invented for physics. If you look at the history of the math that you learned in school, the majority of it was developed for use in physics and engineering. And actually, when I was a college student, I took a whole lot of physics classes in addition to math classes. I thought it was really interesting because it lets you know how to impact the world, so to speak. And so, if we talk about physics, he also used the word mass. And usually when you're rolling something, it's not the mass that matters as much, but it's what's called the center of mass. It's something to do with having things be balanced. For example, if you ride a bicycle, if you have a backpack, is it better to put a very heavy backpack while you ride a bicycle on the back or right here? On the back. Why? What happens if you put it here? Then you tip over, right? So the same notion, maybe you want to have the center of mass to be somewhere in the middle. And that was the very first thing I thought of. So I think this is a solid idea. Except that I took it a little step further and I said, okay, suppose I want the center of mass to be in the middle. Here's a trick question. What's the heaviest side? One. But why? I say it's a trick question because it's not 6, right? It's 1 because 1 has only one hole. So if you have the heaviest side is the 1 and you want to balance it, what side should you put on the other side? Oh, so see, this is interesting. The answer is 1. So I heard 2, 6, and 1. The correct answer is 1, except that that's impossible because if the die is both sides 1, that's not a very good die, right? And the next best answer is 2. That would be the next most balanced. So if the center of mass was the important aspect, actually this is more balanced. 1 opposite 2. And which is the lightest side? 6. So what should 6 be opposite? 5. So you see, actually, when I thought of that, I said, that means everyone got it wrong when they made the dice. See, because they just thought it looked pretty, so they just made it that way. But actually, everyone was wrong. You should make dice this way. And so the real reason I did it in Hong Kong is that was actually the prototype for the new startup company that I started. It's called Dice.com. And all we do is we replace all of the world's dice. It's actually going to be $1 billion company. Here I am in San Francisco, so I should pitch this, right? This is where we're looking for a venture capitalist. We think we can replace all the dice in the world. Actually, that's completely bogus. And in fact, Dice.com is probably taken, and it will probably cost a fortune to buy that domain. But the moral of that story is, if you come up with a new idea and it turns out the world was wrong, sometimes you can turn that into a great opportunity. It just so turns out that in this case, the world wasn't quite wrong. So it is true that the center of mass would be more balanced with this die. Unfortunately, the impact that that has on the dice rolling is, it's bigger than the impact of the moving black holes, which are 4 billion light years away, but it's not big enough to notice. So it turns out there's another explanation beyond that. And that's the explanation that I came up with that caused me to not start this company, because this company would go bankrupt instantly. It turns out that these dice have a fundamental flaw, just because I changed the way the numbers are. In fact, it's so fundamental that if I was playing this game with you guys, my chance of winning is more than half. It's more than half by a noticeable amount. And it has something to do with the fact that these dice are made strangely. So actually, it's not true that it doesn't matter how the numbers are laid out. I was actually intentionally leading you the wrong way when she said the right answer first. She said, something is wrong because the dice are not arranged in the right way. And I said, so what? How does it change the game? And everyone says, yeah, it doesn't change the game. That's the wrong answer. It changes the game completely. There's something you can do, or I can do, with these dice. Oh, this guy, third from the row. What do you see? Here comes a microphone. Here come two microphones. Pick your favorite. Oh boy, there's even two people. Okay, you go first.
If you kind of roll it in, if you put the 1 and 2 on the sides, and then you roll it kind of that way, and then you always have a minimum 3. Like
So-
you always roll a minimum 3.
So did everyone hear that? What he said is, why not just put the 1 and the 2 on the sides and roll it like a bicycle wheel? On an axis, where the axis is 1 and 2. And you'll never get 1 and 2. In fact, the only things you'll get are 3, 4, 5, 6. How would you like to play this game if you're always getting 3, 4, 5, 6 and the other person's just like getting whatever? 1, 2, 3, 4, 5, 6. Who do you think has the advantage here? You, the cheater, somebody said. Cheater, this is a deep question. Is this a cheater or not? Okay, we already got the answer, so we don't need another answer from here. But, yeah, so it turns out that this is a huge advantage. Huge meaning. If you just play this even like 4 times, you'll notice that the probability of winning is much higher for the person with 3, 4, 5, 6. If you play this 100 times, your chance of winning is way over 99%. That's how statistics work. That's why you should never go to a casino. Casinos are set up in a way where their games are just a little bit unfair, like by a few percent. But they play millions of games, and they definitely end up ahead. This thing is actually more than just a few percent unfair. And in fact, if you play this enough times, you'll just run away winning this game. So now there's another comment. Somebody said cheater. Well, you see, that's why I was so precise about the rules of the game, right? I said, you are not allowed to do this. 6. Cannot do that, right? But I never said you have to roll a die in any particular way. So actually, that wouldn't be called cheating. In fact, in this game, that would be entirely within the rules. When you play any game, that's entirely within the rules, unless the rules specifically say don't do that. So actually, the reason I brought people up here to play this game is to demonstrate another fact, which is when you go up to do something, sometimes there's more beneath the surface that you might not realize. For example, if the first thing that had happened is everyone looked closely at the dice to go and see what kind are they. If you had come to this realization, you could actually come up with a strategy and win the game. In that sense, the game is still actually fair. If nobody knew what to do beforehand, but everyone had the same chance to think about it and to follow the rules exactly, but to come up with a better strategy, then they end up ahead in life. So this game actually serves as a little example of what you can do in the real world. Actually, in the real world, life is a game. Life is a very complicated game with lots of rules, and you have to follow them or else you go in jail. Right? There are rules, and you follow the rules. But does it mean that you play the rules with the dumbest strategy? No. It means you go and find out the best strategy to move forward through life. And sometimes that involves thinking carefully about what's going on, and maybe using like this math idea to figure out what to do. But wait, I want to take a little bit closer look at this strategy. You see, there's some more I can talk about here. You said put the 1 and 2 so that it rolls like a wheel. But I have another way. I have another way of winning this game. Just practice enough so that every time you throw, you just get a 6. Right? Why not? That should be doable too, right? That's also like saying the Golden State Warriors are overrated. I already have solved basketball. All you have to do in theory is wherever you are with the ball, you just throw it into the basket and it goes in. I can solve it in theory. Well, unfortunately, practice is also very important. So the second piece I want to ask is, how easy is it to turn that theory into practice? How easy is it to actually roll the die so it stays with the 1 and 2 on the axis? Is that easy, or is that as hard as throwing it and getting a 6? Let's find out. Does anyone want to volunteer to try? It's okay if you fail, it might be hard. I want someone who hasn't been here before. Where are we over here? Oh, I see. Did you try to raise your hand there in the middle? No, you didn't? Okay, I want some more on this side, because I did a lot from that side. You're waving, come on. Okay. So we'll give you 2 shots. Here are the dice. I'll give you 2 tries with the dice. Let me get the water off the table. So 2 tries with the dice. Let's do it this way. Put the 1 so it faces the audience. No, you stand there. Make it so the 1 side faces the audience, and that's how we'll know that you've succeeded. right? Because the 1 should stay facing the audience. Go ahead, you get 2 tries.
Fail.
He says fail. It's okay. It was the first try. It ended up with the 1 on top. Let's try again.
Fail.
It's okay. Good try. Good try. Thank you. We'll look at other things in the try. So he got a 1 in 36 shot with 1 and 1. So let's try again. Now I want somebody from this side who hasn't been up front yet. Who hasn't been up front yet? Maybe if somebody like, oh, is there someone in that room? How about there? Right there. In the greenish thing. Yeah, the greenish thing. Come on. Yeah. Which side? You coming up from this side? If you're coming up from this side, I'll put the dice down here. I don't know what to call the color. Is it green? Is it yellow? Is it safety yellow? Okay. Great. So I give you 2 shots. The 1 faces the audience. Make it kind of roll. Ooh. It's like bowling. Yeah, sort of. Try another one. Okay. Looks like this is harder than we thought. That actually worked. Yeah. Okay, good. Okay, thank you. Okay. Now this is kind of interesting. So we have now seen a demonstration that it might be possible. It might be possible, and it looks like you can do it with some success rate. But actually what I'm going to say is already, once you know that you have a decent chance of making it roll on that bicycle wheel, if it's either it does that or it's like nuts, you still have an advantage. Because when I say it's like nuts, I mean just whatever, you get some whatever number. But if you get a little bit of chance of being biased to have 3, 4, 5, 6, you already have an advantage. To save time, since this talk is not super long, I'll share with you some ways that I know how to do this, okay? Just because it is actually possible. There are effective ways to do this. And these I've learned by giving these talks. I learned from the creativity of the audience. Whenever I teach anything, I don't like to just tell you how to do it. It's not that I have the best way in the world to do anything. I just serve as a moderator for your ideas. And I learn what ideas come, and I bounce off of them. And here's a technique I learned from an audience once. The dice rolling technique holds the die like a diamond. And it comes down sort of like an airplane landing. Okay? And it's done in a way where it's coming down like this, and then you let go as it gets close to the table. And it does something like this. It actually worked. There's a 1 here. I apologize, the table is high, so you can't see it rolling. But effectively what happens is it just comes down like a diamond. It hits the table, and it just starts going in a straight line. Does anyone know why to make it come down like a diamond? Let's go here in the middle. Yeah.
I think it's because the axis can form an axis, so it bounces. If you make it slightly towards, if you center of gravity slightly away from the axis, then it will push it towards a flat side, which will make it roll.
Okay, so that general idea is correct. You're trying to make it roll, right? So just in the interest of time, that was close enough. We have more things we want to talk about, so don't worry. There will be more chances for people to talk. But effectively, it's so that as it touches the table grabs it, and then it just starts rolling immediately and it goes forward. And that's one way. It just looks a little suspicious. Right? There's another way. It's inspired by, I like to play ping pong. And if you play ping pong, I see some other people also like to play ping pong. There's a way where you can make spin on the ball. Actually, the spin is a very important part of the ping pong game if you play ping pong. Do you know how to make the ball spin? What do you do? This kind of thing. Actually, let me share with you a very fun spin. If you can figure out how to make the spin so that you do this, so that when the ball comes at you, you like under the table, do this kind of a spin, like this move. It makes the ball go up over the table with an axis of spin, where the axis is pointing right at the opponent. So they can't really tell that it's spinning. In fact, as it goes through the air, it just kind of does this until the moment it hits the table. And when it does this. Because it's spinning really fast. Does that make sense? It's like, this is not a forward spin or a backward spin. It looks completely innocent. But it lands on the table, and it's very satisfying. Because you watch the other guy go air. You know, the other guy thinks it's so easy, and just does this as hard as they can, and they just hit air. It's really, really funny. Anyway, so that's a good spin. But that's the one I wanted to use, right? So I wanted to go and make this die spin first by doing the same kind of motion, like this. Except I don't toss it in the air. I do it so that I grip it with these 3 fingers, roll it, and then let go. So this is already gripping with 3 fingers, doing the twist, and letting go just as I get to the table. And then it just goes across. Actually, that won't work. I'm just going to push this straight across. The front row can see that's a 1. So you just kind of do this. Somebody said you want to go to Vegas and do that. Actually, I tried. If you do that, you get asked to please leave. So actually, in Vegas, if you look like you know what you're doing, they just ask you to please leave. This is another reason you shouldn't bother going to casinos. Because in casinos, the moment you start winning, they notice and they ask you to please leave. It's just not fair. If you want to do that kind of thing, figure out how to trade on the financial markets instead. Nobody will ask you to please leave. Right. In any case, this is actually entirely doable. If you practice, it's extremely easy. And so now at this point of my talk, since I've just talked about these practical techniques, I need to give a very clear statement. Please, do not use anything you've learned today to cheat other people. Please do not use anything you've learned here to take advantage of other people. This is a serious statement. I did not come here to teach everyone how to take advantage of other people who don't know about these techniques. Because the vast majority of the world does not know, so they would all be suckers. Do not do that. Actually, the point of me using this topic is because everyone in this room has touched these dice before, and everyone can appreciate how this is a huge advantage in all sorts of games that you play. And that's why I choose this topic. But do not use knowledge you've learned just to cheat other people. That doesn't make the world a better place. In general, we're trying to get knowledge so we can make the world a better place. In fact, I work at a university. Some people often ask, why do university admissions care about things like community service? Why is it important to be a good person? Why can't I just be smart? I'll tell you why. If someone just wants to be smart and wants to take advantage of other people, they're better off stupid. The world is better off if that person is stupid and not able to cause trouble. In fact, what we want in our educational institutions is to help the people who want to do something good for the world. To go, we need volunteers, right? Do something good for the world to get more capable of doing more good for the world. Not just get a bunch of people who want to take advantage of everybody else. Those people we don't want to teach. So that's why this particular thing is, yes, I showed you a technique. See if you can use this technique to do something fun and good with it. Okay, so now we've just talked through this dice thing. And indeed, with these dice, you can actually get a huge advantage. So that's actually one reason why dice are not this way. Actually, my full theory of why dice are the way that they are is that if dice were in this way, mathematicians would have come around and found a way to exploit them. But it turns out the only kind of dice that you cannot exploit this way are the ones with 1 opposite 6, 2 opposite 5, 3 opposite 4. Why? So far we've only proved why these are bad. We have not proved why it should be opposite sides add up to 7. Think about how we can use the same kind of ideas to explain why it has to be how it is. I'm going to unlock the computer and then we'll be able to draw it on the screen. I switched to my chalkboard. So I'm going to draw a die. Can you see this? This is my die. Can anyone think of a way to explain why it should be that the opposite sides add up to 7? Yes?
Because, like, if you prevent yourself from getting the lowest number 1, then if 6 was opposite, it would also not be able to 6.
So what she said is, look, suppose somebody is trying to cheat, or cheat is the wrong word. Suppose someone's trying to take advantage, and they're trying to not get 1. Then they put 1 on the side. Well, then you force them to also not get a 6 by putting 6 on the other side. And somehow that makes it so they have no advantage from having no 1 because they also have no 6. How do we quantify the advantage? Here we are actually trying to think, you're right, but how do this is where math comes in. How do we know that that's the right way to give them no advantage? You seem to have an idea over there in the 4th row.
Like, the average, if you take out 1 and 6, it's still 3.5. But like, for the unfair dice, if you take out 1 and 2, then the average becomes 4.5. So then it becomes unfair.
because you have a like higher average than the other person.
So that's the kind of concepts I want to use, and I'll just write it down quickly. It seems like both of you are going at notions of average. That's how you're measuring how fair something is. And in fact, we're thinking about what happens if you roll the die like this, like a wheel. If you roll it like a wheel, it seems like everyone agrees you need that the average of these four sides, what do you need the average to be? You need it to be the same as the average if you just randomly threw it, right? Well, if that's the case, then what do you need the sum of those four sides to be? Yeah, in the front. Of the four sides, how did you get the 14? 3.5 times 4, because that's how you go from sum to average to sum, sorry. So the sum is 14. Now, from all of that, you should be able to conclude something about what you need the sum of the other two sides to be. How do I know what the sum of the other two sides has to be now? What do I do? You seem to want to say something. Yeah? 21 minus 14. The sum of all the numbers, 1 plus 2 plus 3, thank you, that's perfect, plus 4 plus 5 plus 6, minus 14. Because all the numbers are 1 through 6 anyway, subtract 14, 7. And that's actually why the opposite sides of a die need to add up to 7. So this is the explanation that I ended up coming up with, that because of this setup, with the regular dice, those are the only dice that you're not able to go and use these advantages on. Did that make sense to everyone? Because now you're also all in the know. What if you spin the die, you mean on the corner? Yeah. Yes. What if you spin it on the corner and just hit 4, 5, 6? What I'll say is, I have not seen anyone who's able to pull that off. See, this is where we're talking about theoretical and the practical. The theoretical of this roll as a bicycle wheel is easy. Even I can do it, and I can't shoot free throws. But the spinner on an axis, that's actually very hard. There's another reason why that's very hard. It's because physically, if you're spinning it like on an axis like a top, at the beginning it's under control. But after a while, the spin slows down. As the spin slows down, it actually starts to go in some chaotic directions. The reason why this rolling like a wheel works is because as it slows down, it's still rolling forward. So it's not going to bounce either side. That's all. Okay. I want to use some of the time to also talk about then another game. This other game is also kind of fun. For this other game, we're still going to have 2 players. And we're going to, this time, switch from using these fake dice to real dice. So I brought here some dice that I know are fair because I went to Amazon.com and I searched for casino dice. So these are as fair as they can be. These are the dice that they use in casinos. You guys don't seem to think that means they're fair? Actually, I'll give you a proof why they're fair. The reason why casinos want to have fair dice is because the games are unfair. And so the last thing the casino wants is that there's an unfair game with unfair dice, and minus times minus is plus. Yeah, so these are actually very, very fair. They're so fair that the dots don't even have holes. They're actually just like painted on, with like paint that looks just like almost no weight or something. And they're even sort of translucent. So you can see there's nothing inside them, as fair as they can be. So I want to switch the game into a game with completely fair dice, but I just want to change the rule very slightly. Each person's going to get 4 numbers. Does anyone know anything else you can do with 4 numbers to figure out who wins? Can anyone suggest something? Let's take someone on this side. Oh, over there in the front row. Do we have a mic? Oh, just yell.
Like the average?
We could calculate the average instead. But actually, in this case, the average and the sum would give the same winner, because both I divide by 4, right? So is there another game I can play? Is there anything different from average? Let's go to this side. Do you have a microphone over here? Somebody reachable. How about the orange shirt? Yes, you're wearing an orange shirt. I love how everyone looks now, because I also don't remember what shirt I put on in the morning. Okay.
Maybe you could take like whoever won the most separately.
Whoever won the most separately. That's one way to do it. That is one way to do it. And in fact, that would have been a third game I played if we had the time. Is there anything else we can do with 4 numbers to just decide who wins? Let's go back to this side of the room. Somebody who hasn't answered as many questions yet. More, just choose someone who hasn't answered as many yet. And then when you have the microphone, please stand up.
You could multiply the numbers.
You can multiply the numbers. Okay, here's a question. How many people here were thinking of saying multiply the numbers? Good, good, good. Because that was my next slide. Right, so as you can see, I'm reading minds very well. I'm just coming up with the most natural, most basic games you could try to play. We did the sum, now it's the product. So it's going to be the same setup. 2 players, roll 4 times. Same thing we saw, switch dice every time. This time we get 4 numbers, you multiply the 4 numbers, and see who gets the bigger product. Does everyone understand this game? Could I have 2 volunteers, please? In the back there is a dark blue thing. Yes, you with the white, there's some white spot. Yes, you. Yes, please, yes. Okay. And somebody representing this team who hasn't been up yet. Where do we have? Have you been up yet? You haven't been up yet. Come on, please. Okay, great. Okay. And now we also need, looks like we got extra people. There's no problem. We need scorekeepers too. Okay, so I guess you're rolling?
Oh, sorry.
I actually had pointed at you. Are you good with multiplying? Are you good at multiplying? You want to multiply? Come, please, we need your help. Yes, come back. You already started multiplying, you'll come back. Oh boy, this guy doesn't trust me. Okay, and we need one more person here who's good at multiplying. These numbers do get big, so be aware. Did you want to multiply? In the white? Yeah, come on, multiplying. Okay, so you're multiplying. Okay, so you think it's okay?
Oh, there's dents on the 6.
There's dents on the 6?
Yeah.
Okay.
It says 23. It says 23 on it.
Yeah, it's the serial number of the dice. Actually, casinos like to put serial numbers on their dice so they know how many times they've been rolled. That way they can keep changing the dice. So you're keeping score on the set, please stand on this side, okay? Product, and you keep score on this side, right? Let's just go ahead. First round, go ahead. Okay, and you switch dice. Okay, and now let's report this score. Over here.
4.
1.
4 versus 1. Second round, let's go.
20.
Are you sure?
Oh, that's his dice. Yeah. This is mine. So 20. What is 5? I had 4 last. Oh, that's 16.
Yes, this is actually quite hard. This is why I asked other people to help. So it's 4 times 4, 16. This side?
2. Wait, 1 times 2.
Ah, 2. It's still 2. So it was 1 times 2 is 2. 16 versus 2. Third round, let's go.
64.
This guy likes 4s.
Wait, this is 4. Wait, that was 2. That's
Yeah.
4.
So it was a 2, so now it's 4. 64 versus 4. Alright, let's go one more time.
There's a 3 over here.
That's 192.
3 was here, 192.
And there's a 3 over here.
3 over there, so it's 12. Okay, great. But actually, who wins and who loses is not so important. Actually, I will also say, even though the scores look very far apart, they're not that far apart. What you just learned is when you multiply, things get big really fast. That's all. The only reason it sounds like such a big difference is because we're multiplying. But again, who wins and who loses is not important. What's more important is the game. For this, actually, this is all I need for experimentation. So you guys, if I can say, please go back. Thanks for being brave. Yeah. And again, don't worry about who wins and who loses. Those are completely unimportant. But the one huge lesson here was multiplying makes things absolutely huge. And it's not like somebody had a huge advantage. It's just that they multiplied some numbers. And this is a life lesson. If you can ever get involved in things that multiply, that help you, it's great. This is why you invest in the stock market under normal circumstances. And then somehow multiply your money. This is also why you don't try to get in debt and multiply your debt, right? So multiplication is cool. But I wouldn't bring this game unless there was a way to win it. Actually, there's a good strategy here. This is the normal die. This thing I put up here, these are normal dice. How should you play this game? This game actually sounds completely reasonable. It doesn't even use special dice from Hong Kong. It uses the most fair dice that you could find. But it has a fatal flaw. There's a way to play this game to have a better than half chance of winning. Oh, I see. Somebody sees something. Over there in the yeah. What do you see?
So if you take out the 1 and the 6, do the same bicycle wheel trick. Just when you multiply by 1, the score doesn't really change. So therefore, you can take out the 1, so you don't change, and take out the
Okay, so I'm hearing this idea. He's saying he hates the 1 because that's what hurt us a lot in this last game. 1 hurt. So maybe take out the 1, and then you're also thinking, but then I don't get the 6. How do I know that it's a good deal? Here I'm trying to figure out, is it a good deal to lose the 1 and the 6? Let's go here. You were actually in the front also. What do you think?
It's a good deal to lose the 6 because you have a 1/4 chance of getting the 6 if you do the bicycle wheel. But if you do it the other way and you avoid the 1 and the 6, like 3, 4, and 5 are considered big numbers, so you have a better chance with that.
Okay, so there's this other notion of like somehow there are these big numbers. These 3, 4, 5 are already big numbers. We're getting closer to consolidating in something mathematical that we can say. What we're really trying to figure out right now is it worth it to lose the 1 and the 6? And I'll give you a hint. The answer is yes, but there's a way to explain it very precisely. Did you want to say something? Oh, here comes the microphone. What did you say?
You multiply 1 and 6 and you take the average is 3. You multiply 2 and 5 and 5.
Multiply 1 and 6? Okay, so something about multiplying and something about average.
So
Actually, let me just do all of them.
I guess it's worth it because 6 and 1 get those smallest.
Yeah. So that's the right kind of thinking. What she's saying is, look, when you multiply the numbers, right? Like we're not adding anymore, we're multiplying. And if you're giving up 1s and 6s, you're sort of giving up 1 times 6s. We shouldn't think about giving up the average of 1 plus 6 over 2. We should think about giving up multiplying. And if I had a choice, would I rather multiply together 1s and 6s or 3s and 4s? Actually, this is better. So this is the heart of what's going on. In fact, this is in a lot of middle school math contests. It's like something like, hey, I've got a mile of fence. How do I make a rectangular fence that has the biggest area? It should be a square. You've learned this. You've learned that if I've got numbers and I smush them closer together by the same amount, then the product gets bigger. It's a very fundamental fact. In fact, in high school, if you do proof-based math competition, it's even called the arithmetic mean, geometric mean inequality. Actually, when I came up with this whole talk, once I realized that I couldn't go to Vegas and cheat anyone, I said, oh, but it's okay. Actually, if you go to the normal dice, because products and sums behave differently, this game is going to have an advantage. Boom, just like that. And I also use the word geometric mean. Again, this I know that the audience here is not all the same age, but for some people you have learned about a notion called geometric mean of two numbers, A and B. What is it? Does anyone know this? Yeah? Square root of AB. And when I first learned this fact, I remember asking, why are we learning this fact? Like, who cares? What do you ever use the geometric mean for? Yeah, I don't know. I know what you use the arithmetic mean for. You take a bunch of tests and your grade at the end of the semester is the arithmetic mean of your score. And I was always wondering, why would anyone ever use the geometric mean? Huh? There's a theorem in geometry, he says, where if you draw a right triangle, like this, where it's a right triangle, and this is a right angle, and this is, say, 9, and this is something like 16, then this is the geometric mean, which is 12. There's a theorem in geometry that lets you do that. That's something called bits using similar triangles. Can be done that way. But ultimately, I brought this up because this problem lets you use the geometric mean. The geometric mean is an average. But it's an average in the context of multiplication. So actually, why we care about the normal arithmetic mean is we usually add stuff up. And then the arithmetic mean says how much are you adding from each of them on average. The geometric mean, on the other hand, tells you how much you're multiplying on average. You see, we were using the word average of saying multiply by 1 and multiply by 6. So on average, I multiply by how much? I'll tell you how much. If you multiply by 1 and then multiply by 6, then on average, you've multiplied by square root of 6. Does that make sense to people? I heard it, oh, because the idea is that I'm multiplying, and I'm saying first times 1, then times 6. It should be like saying times something and then times the something again. And that something should be the square root of 6. That's what this geometric mean is. The geometric mean of AB is times A and then times B. That's the same thing as times square root AB and then times square root AB again. And so what's really going on here is that these three products, the biggest geometric mean is 3, 4. And so that's why the secret to that game is actually you should put the 1 and 6 on each side. If that was a little bit over your head, I have another way of explaining this that's more easy to grasp immediately, which is if you had not 1, 2, 3, 4, 5, 6, but if you have 0, 1, 2, 3, 4, 5, does anyone know what's a good strategy? No 0. So you just put the 0 and the 5 on each side. Great, so that's the second game. The last game I don't have time to actually really play through because the last game is one which actually takes an hour to play. But I'll talk through it really quickly in about 5 minutes. This last game is called Monopoly. Oh, so people have played this Monopoly game before. Now, in Monopoly you roll 2 dice. And then what do you do? If I have a 1 and a 2, what do I do with this? 3, you add them together. You go 1, 2, 3 steps forward. If you take 3 steps forward and you go onto your enemy, if you go onto your opponent's hotel, is it good or bad? Bad, because you have to pay money. And actually, how do you win or lose this game? Bankrupt, you lose. Don't run out of money. Does anyone know any great strategies for playing Monopoly? Any secret strategies you use over there? Yeah. Just shout because we're short on time.
Just buy everything you can, because even if you go bankrupt, you can still mortgage them.
So he said, just buy everything you can. He said, because if you go bankrupt, you can still mortgage them. Actually, I'll say the heart of that is the true strategy. Indeed, in Monopoly, buy as much as you can, because later you can do whatever you want with it. And unfortunately, that was also the best strategy in real life for the last 30 years in terms of property. Unfortunately for the rest of us who are the younger generation. Okay, you have another strategy. Yeah.
So if you roll 2 dice and add the sum together, somebody calculated the most likely outcome is 7. So using this, you can figure out what tiles will people most likely to land on, and then invest in those to get maximum outcome.
Great. So again, because of shortness of time, I'll stop with these suggestions. This in particular is yes, 7 is the most common outcome, and in fact, that means the most common place to land is actually 7 squares after jail. Because jail is the most common square to land on. There are many ways to get to jail. There's a square saying go to jail. You go to jail. There's some card, like a yellow card, I think, says go to jail. There's some red card, orange card says go to jail. You could even just have walked on jail and said hello to the people nearby. There's 4 ways to get to jail. So the thing 7 away from jail, around there is the most common. Actually, I should also say there's another strategy in Monopoly. The best thing is you first buy everything you can. That's the beginning of the game. The end game is once there's nothing left to buy, attempt to just be in jail for the rest of the game. And unfortunately, some people also do this strategy in real life. Okay, right. So, now, about Monopoly though, I thought of a very interesting strategy which I had not seen other people do before. How often has anyone ever experienced this when you're playing Monopoly and you're saying, I'm here. I really don't want to go there. 1, 2, 4, 5, 6. I really wish I don't get some number. Has anyone ever experienced this before? Okay, lots of people. Tell me a number. I will not get that number as the sum of my 2 dice. Tell me a number. Oh, I won't get 13. That's easy. Okay, tell me another number. I won't get this number. Yeah. 5. What? I will not get 5 as the sum of my 2 dice. I will not get 5 as the sum of my 2 dice. I have a 4 so far. Oops, actually that one fell off. But in any case, I didn't get a 1. Does anyone know what I was doing? I just put the 1 on the side, darn it. So there's no way I'll get the 1. Did that make sense to people? If I know what I don't want, I put it on the side. I won't get it. Okay, so please do not use anything you've learned today to cheat other people. This is not the point. This is not to cheat other people. Once you know this to tell other people, you can have a more fun game of Monopoly, where it turns Monopoly from a game of chance into a game of skill. In general, with the talk we had so far on the math part, I'm going to rotate to another topic real quick after this, and then we'll switch to Q&A. But on this topic right here, we watched us go from a theoretical question. Why do opposite sides of the die add up to 7? Purely theoretical, no idea why. We're thinking about it just to understand. Once you understand the world, then you can start to figure out how to change it. And then at the end, we walk with that understanding from something we had no intention of applying into something which we could figure out, oh my gosh, everyone in the world has played Monopoly, but no one's ever thought of this before. How can that be? And that's showing you this way a mathematician can look at life and see interesting things. We're short on time. I want to make sure there's time for people to ask and answer questions also. But there's a few other things I wanted to briefly touch on. One of them is about maybe technique on learning mathematics, and another one is about resources, because these are different topics that are more practical. So, if I roll back to here, learning mathematics. We actually just had a talk here where we apparently didn't really learn much mathematics, although actually maybe we did. There are different ways to learn. One way to learn is to systematically just say, I want to learn this topic, then this topic, then this topic, and after a while I can do every kind of problem in the world. That technique is based on doing tons and tons of problems until you've done every problem type in the world. This is effective. It actually works. But there's another way to learn, which is to learn how to think. The entire point of this talk was to practice thinking. This is actually something I experienced when I was young, growing up in America. I, of course, did practice, but something we also did every day, in my household, was my father would always bring a challenge question of the day. And we'd think about that for 15 to 30 minutes. And just try coming up with ways to solve something where we don't know what to do. That is what I intentionally brought here today. And my feeling is if you complement both of these, the one part you build this foundation, which is cool, very important, but the other part you spend enough of your time attacking questions which are actually new for you, where nobody's feeding you a technique, but instead you have to come up with it. Then you learn how to think and adapt to any situation. And then in the end, any math, any science, any technology stuff becomes very, very easy. To this end, if we were talking about learning resources, sometimes parents or students are asking, where do you find resources to try to learn these kinds of things? I can say, one thing, we actually have a bunch of handouts that we collected a bunch of resources that we can, anyone wants to pick up afterwards, this. But I want to briefly talk through a few of these, which is for people who are middle school age or elementary school age. I strongly recommend a book which is called Competition Math for Middle School. That's actually listed on the thing, on the handout. This book is excellent. Oh, somebody already brought it. This is like the book to practice learning this kind of mathematics. Yeah, it looks exactly like this. That's the one, and I didn't ask him to bring it. This shows how fundamental it is. In fact, we use this book even when our kids are like in elementary school. There's no reason that we need to wait until we have practiced all of the 2-digit multiplication drills to be able to start thinking about mathematics. If you're in high school and you haven't played with this stuff before, don't let the title turn you off. It says middle school, but most middle schoolers in America can't do it anyway, right? It's actually hard. Now, that's one source. Another source that we often point people to is that you want to learn by finding questions. And one way that you can find lots of questions is online. There are all of these old exam questions for the AMCs and the AIME. These are the middle school and high school math competition questions. These are an amazing resource because the amount of work it takes to create the questions is very intense. Whenever people are making these questions, they try very hard to make questions that are not normal. In fact, whenever we're making questions, if we say, oh, this is a standard question, that's the kiss of death. The question doesn't make it. We intentionally want to make questions that will make you think. And so there's a treasure trove of these questions that have already been created and already been put online. These are excellent resources for people who are self-motivated and who can go and try to learn through those old questions. All those answers are also online as well. Now, when it comes to other things, like suppose you want more guidance, you're very lucky you're in this area, in the Bay Area, where there are lots and lots of opportunities for you to be able to go and learn in person with people who will teach you mathematics. That's not something I had. I grew up in Madison, Wisconsin, where there were not such opportunities everywhere. So I would actually advise that if you can take advantage of these, that's in some sense one of the best ways to be able to learn a huge amount. Lastly, I want to comment on something else which people have also asked me about. So I used to give all of these talks, and then people would sometimes ask, do you have any way of maybe providing some way of teaching? And for a long time, my answer was, no, unless you're in China. Well, the reason is because for 3 years plus, I've actually been running online courses in China. That's one reason I actually just came back from China. But at some point, I thought that's a little bit odd because I'm based in the United States, and all of those courses in China are also in English. So I actually very recently, over the summer, launched an entire series of the classes in the United States. These are not the same as attending in person to go and learn from a teacher right in front of you. But I created this to provide a way for people to be able to fight with questions actually on a daily basis. Sort of the same thing I experienced when I was a kid growing up with my father providing these questions. And because these talks, the talks that I give around the country, these are actually sponsored by the Daily Challenge which I run. I usually make a few comments about this. So this is actually a new series that has just been released. And this is now a new resource that I add to the list of resources that exist, where the objective was to think about how to take all of middle school mathematics and not teach it systematically, but to teach it intentionally unsystematically, but in a right order. So what I did is I actually created a list of daily challenges where the questions are designed so that you shouldn't know how to do the question when you look at it, but you should have a chance of figuring it out if you think. Because I think actually one of the best ways to learn is if you constantly fight against something which is above your level, which you have some chance of beating, and a hint comes after a minute or 2 minutes. But you get to discover how to solve it yourself. So this is this daily challenge. We're releasing this to give an entire year's of coverage of different math topics in the middle school math competition area, but also relevant to anyone trying to learn, say, combinatorics or any of those things you see in the high school competitions. So this is something I'm happy to talk much more about later if people have questions. But ultimately the goal was to try to find a way to provide a complement to what you find in systematic education, to have something which looks not systematic, but actually is. Because what happened first was a complete deconstruction of the kinds of things that you learn in middle school math competitions, and reconstructing it as its own syllabus, where it can be entirely driven by working on problems, instead of just learning techniques which are fed to you. So that's the main part of my talk. I will say anyone who wants to maybe follow any of the things that we do, we actually do have a WeChat public account, which we release various comments about mathematics and other kinds of things about learning, which is the best way actually to keep in touch. But now, I wanted to give enough time to be able to answer any kind of questions that anyone might have in the audience. These questions can range over anything. I would prefer that they are not all about how to play dice. In fact, when I come to a place, I prefer to be able to answer questions about just about anything. Learning mathematics, growing up. If the students have questions about like growing up and being a mathematician, if you want to talk about technology, I actually have a wide range of interests. These days, in addition to being a math professor at Carnegie Mellon, I also am working in online education, both in the United States and China. And at the same time, I also do a lot of computer programming things, because that's what's involved in a lot of online education. So I'm happy to take